If you set Voyager 1, the fastest probe humanity has ever sent into deep space, traveling at nearly 17 kilometers per second on a direct course toward the nearest star to our Sun, it would arrive in approximately 73,000 years. 73,000 years. That means if Voyager had launched at the very moment the first anatomically modern humans were arriving in Europe, it would still be decades from its destination by the time you finish watching this video. And we are talking about Proxima Centauri, our closest stellar neighbor, sitting just 4.24 light-years away. A distance that, on the scale of the Milky Way, is the equivalent of 2 grains of sand placed side by side on a beach stretching 10,000 kilometers. Proxima is literally our nearest neighbor in the cosmos, and even so, it lies so far away that our finest machines would need a span of time greater than all of recorded human history multiplied by dozens just to reach it. That proportion between relative closeness and absolute inaccessibility is the starting point for understanding why an interstellar spacecraft is a challenge in an entirely different category from anything human engineering has ever attempted to solve. This is not about building something bigger, more powerful, or more resilient than what has come before. It is about solving, simultaneously, multiple problems that belong to entirely distinct physical domains: energy, structure, biology, time, relativistic physics, where the solution to each one frequently makes the others worse. Solving the propulsion problem may deepen the radiation problem. Solving the mass problem may compromise the crew's protection. Every solution carries a cost that must be paid somewhere else, and the equation never balances simply. It is this deep interdependence between the problems that makes the interstellar challenge so peculiarly difficult and so revealing about the true limits of what physics will allow. For a journey within a useful human timescale, under 100 years, a craft would need to travel at least 10% of the speed of light, equivalent to 30,000 kilometers per second. For a sense of what that means in practice, the distance from Earth to the Moon is 384,000 kilometers. At 10% the speed of light, you would cover that entire distance in just over 1/100th of a second. The New Horizons probe, which flew past Pluto in 2015 and is among the fastest human-made objects ever to move through the solar system, traveled at around 14 kilometers per second at its peak velocity. To reach 10% the speed of light, a spacecraft would need to be approximately 2,100 times faster than New Horizons. Not 2,100 times larger or more expensive, 2,100 times faster. And when you begin to calculate the energy required to achieve that, the differences stop being linear and become exponential in ways that quickly reveal why this problem is structurally unlike anything we have ever attempted. The first fundamental obstacle to emerge is the equation that governs every rocket formulated in the 19th century and merciless to this day. It describes the relationship between a spacecraft's final velocity, the exhaust velocity of its propellant, and the ratio between the vehicle's total mass and the mass of the craft without fuel. What it reveals, when applied to interstellar velocities using conventional chemical propellants, is something most people never see coming. To accelerate a school bus-sized spacecraft to 10% the speed of light using common chemical fuels, you would need a quantity of propellant that exceeds that of all Earth's oceans combined. That is not narrative exaggeration. It is the direct result of the mathematics when real numbers are placed into the equation. Chemical propulsion is out of reach, not because it is outdated technology, but because there is an absolute physical limit to the energy that molecular reactions can release per kilogram. And that limit sits many orders of magnitude below what interstellar velocities demand. This redefines the problem in the most decisive way possible. It is not a matter of improving what already exists, but of accessing radically different forms of energy. Nuclear, electromagnetic, antimatter, or something that has not yet been built at any functional scale. And when you begin to examine each of these alternatives with genuine scientific rigor, what you find is always the same underlying structure. Every solution resolves part of the problem, while revealing a new layer of difficulty that was invisible before. This is why, more than 60 years after the dawn of the space age, not a single interstellar spacecraft project has moved beyond theoretical proposal to something with a realistic chance of being built within the next century. The problem is not one of ambition or resources, it is one of physics, and understanding it in depth is the essential first step toward any real progress. What makes all of this genuinely fascinating, rather than merely intimidating, is that each layer of difficulty is, in itself, a frontier of human knowledge that has never been crossed under real conditions. Every obstacle that emerges when you attempt to design an interstellar spacecraft is, in practice, a question about how the universe behaves in regimes we have never explored. The history of physics is filled with problems that seemed insurmountable, right up until the moment someone asked the right question. The interstellar challenge may be the greatest humanity has ever contemplated, but it may also be the one that forces us to learn things about the universe we could never have discovered any other way. Nuclear propulsion was the first serious alternative to chemical rockets for interstellar travel, and it represents a genuine leap in energy density. Nuclear fission, which splits heavy atoms like uranium or plutonium to release energy, is roughly 1 million times more energy dense than the most powerful chemical reaction ever known. In the early days of the space age, projects like Orion proposed detonating nuclear bombs behind a spacecraft to propel it forward in successive bursts. Simulations showed that an Orion vessel could, in theory, reach between 3% and 10% of the speed of light, which would already place a journey to the nearest star in Centauri within a time frame of just a few decades. The concept was physically sound in its fundamental aspects, but the central problem was devastating. The spacecraft would need to survive the detonation of a nuclear bomb every few seconds, for hours on end, just to reach cruising speed. No known material can withstand the cumulative punishment of repeated nuclear explosions in rapid succession without disintegrating before it ever clears the solar system. Nuclear fusion, the opposite process, which fuses light nuclei, like those of hydrogen, to release energy, the very same process that powers the sun, offers even greater energy per kilogram than fission, and without the most hazardous radioactive byproducts. The Daedalus project, developed in the 1970s by a team of British engineers, proposed using helium-3 and deuterium fusion to propel a robotic spacecraft to roughly 12% of the speed of light. The analysis revealed promising physics, but there was an immediate and defining problem. The quantity of helium-3 required for fuel exceeds the entire available supply on Earth by many orders of magnitude. Helium-3 exists in more abundant quantities on the surface of the Moon and within the atmospheres of the gas giants. But extracting it at a scale sufficient for an interstellar mission presupposes decades or centuries of space infrastructure that does not yet exist, even in outline. A pattern emerges here that repeats itself across virtually every advanced propulsion concept ever proposed. The physics works on paper, but the engineering required to realize it presupposes prior technological developments that have not yet occurred. Laser sail propulsion eliminates the onboard fuel problem with elegant simplicity. A sail driven by a high-powered laser beam fired from Earth or an orbital station could, in theory, accelerate an extremely lightweight structure to a significant fraction of the speed of light within minutes, carrying no propellant whatsoever. The breakthrough Starshot project, announced in 2016 with real funding of hundreds of millions of dollars, proposes exactly that, sending nanoprobes equipped with ultra-thin sails toward Proxima Centauri, driven by a ground-based laser array with combined power on the order of tens of gigawatts. The calculations show that the nanoprobes could reach roughly 20% of the speed of light, arriving at the Proxima system in approximately 20 years. The physics is sound, but the engineering challenges are immense. The laser array required would demand power comparable to that of a large nuclear power plant. The sails would need to be manufactured at thicknesses on the order of nanometers, flawless across their entire surface, and the nanoprobes would need to survive passage through the interstellar medium at speeds for which no shielding material has ever been tested. Antimatter represents, within the known laws of physics, the most energy-dense fuel theoretically possible. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass into pure energy, an efficiency no other known process can match. By comparison, nuclear fission converts less than 1% of mass into energy, and the best chemical reactions convert a fraction of even that. An antimatter-powered spacecraft could, in theory, reach velocities relevant to interstellar travel using relatively modest quantities of propellant. The obstacle is that antimatter is extraordinarily difficult and expensive to produce. All the particle accelerators on Earth combined produce, in a single year, a quantity of antimatter that, if fully annihilated with ordinary matter, would release enough energy to boil a few liters of water. To fuel an interstellar vessel, quantities billions of times greater would be required. And no process exists today that would make such production feasible at any technologically conceivable scale in the near future. What emerges from all of this is a stark and lucid picture of the propulsion problem in its true form. Among the alternatives we understand physically, none exist. That is, simultaneously efficient enough, producible at sufficient scale, and structurally achievable with technologies we can conceivably develop within a few generations. This does not mean the problem is unsolvable. It means the solution will likely involve breakthroughs we do not yet possess, or conceptual approaches that have not yet been formulated. And it is important to note that propulsion is only one piece of the puzzle. Even if a working propulsion method were discovered tomorrow, the ship would still need to decelerate upon reaching its destination, which demands an equally powerful second propulsion system. It would need to generate power for all its systems across decades. It would need to communicate with Earth across distances where every message takes years to arrive. And above all, it would need to shield whatever lies within it from an environment that grows progressively more lethal the faster it travels. There is a fact about interstellar space that rarely surfaces in discussions about starships, yet it may be the most underestimated obstacle of all. The interstellar medium is not empty. It contains hydrogen atoms and scattered particles at an extraordinarily low density, roughly 1 atom per cubic centimeter on average, which sounds negligible until you calculate what happens when a ship traveling at 10% the speed of light plows through that material. At that velocity, every hydrogen atom in the ship's path strikes like a high-energy cosmic ray. The particle flux battering the forward hull of a ship under those conditions would be equivalent, in radiation dose, to standing continuously in the beam of a particle accelerator. No shielding material currently known would protect a human crew under those conditions for months, let alone for decades, and the problem scales with merciless precision as speed increases. Double the velocity, and you quadruple the impact energy of every particle, making any solution based on physical shielding progressively heavier and more costly as speed climbs. One approach to the radiation problem is to use mass itself, dense layers of material mounted at the front of the ship to absorb or deflect incoming particles. The problem is that this additional mass must be accelerated along with everything else. which increases the energy required for propulsion, which demands more fuel, which carries more mass, and we are back inside the familiar spiral of the rocket equation. Another approach is to use electromagnetic fields to deflect charged particles, something akin to what Earth's magnetosphere does when it shields us from the solar wind. The idea is technically compelling, but generating a magnetic field strong enough to protect a ship at interstellar velocities would demand an amount of energy that competes directly with the energy available for propulsion. Every solution to the radiation problem creates a new problem somewhere else, and this pattern repeats across virtually every subsystem of a hypothetical interstellar vessel. Time is the second dimension of the human problem, and it introduces challenges that no space mission we have ever undertaken has had to face at the scale required. A journey at 10% of the speed of light to Proxima Centauri would take approximately 42 years. 42 years inside a sealed environment, with no resupply, no external maintenance, no possibility of a swift return in an emergency. Any mechanical or electronic component that failed would have to be repaired using only what was carried on board. And in 42 years, things fail. The International Space Station, the largest space habitat ever constructed, receives regular resupply missions and maintenance visits. An interstellar vessel would need to be, in terms of self-sufficiency, an order of magnitude beyond anything we have ever built, including fully redundant life support systems, medical capability for every conceivable emergency, and systems able to fabricate or replace any critical component using only the materials available on board. Human biology presents its own set of limitations, ones that the space environment exposes with particular clarity. In prolonged microgravity, the body suffers progressive muscular and skeletal degradation, fluid redistribution that elevates intracranial pressure and degrades visual acuity, and modifications to cardiovascular function that have been documented in astronauts following long-duration missions aboard the ISS. 6-month stays on the station have shown that full recovery can take months after returning to Earth, and an interstellar voyage would be 7 times longer, and that is only one way. Generating artificial gravity through the rotation of the vessel is technically feasible, but it imposes severe constraints on the vehicle's architecture, its energy consumption, and its structural complexity at high velocities. And even with artificial gravity, the effects of cosmic radiation on human DNA across decades of exposure, far beyond the protection of Earth's magnetosphere, represent a risk that current research is only beginning to quantify with enough precision to guide the design of shielding systems. Long-duration psychology in confined spaces is a field that developed precisely because missions of progressively greater length revealed problems that no one had fully anticipated. Prolonged isolation experiments, such as Mars 500, which confined volunteers for 520 days inside a sealed facility to simulate a journey to Mars, revealed that the most serious problems were not technical, but interpersonal and cognitive. Conflicts that accumulate with no possibility of escape, a monotony that erodes executive function, and the complete absence of any way to break free from the immediate environment. Aboard an interstellar vessel, those factors would be amplified across a timescale that no simulated mission has ever come close to replicating. And then there is the question of authority and decision-making. On a journey spanning decades, the crew becomes progressively more autonomous from any space agency left light years behind, and the governance structures that function perfectly well on missions of months may not scale to the complexity of a decades-long mission without profound adaptations that have yet to be seriously conceived. There is yet another dimension that emerges when the voyage is long enough. In generation ship scenarios, it would be the descendants of the founders who finally reach the destination, having never once laid eyes on Earth. That scenario raises questions that reach far beyond engineering and biology. Questions about the right to bind generations who never chose the mission, about the transmission of enough technical knowledge to keep a ship functioning for centuries, and about what kind of social structure can maintain cohesion inside a sealed environment. Across entire generations, these are questions with no technical answers, belonging to philosophical, ethical, and sociological territories that humanity has never yet had to navigate in any practical sense. And a crude interstellar vessel, if one is ever built, will need those answers before it ever leaves. Faced with all of this, the staggering scale of the distance, the hard limits that physics places on propulsion, the fragility of human biology in interstellar space, a natural question rises to the surface. Where do we truly stand? What exists today that represents real, measurable progress toward that goal? The honest answer is that we are, in terms of actual engineering capability, far closer to the beginning of the problem than to its end. But progress does exist. It is genuine, and it carries a different quality than it did decades ago, because there now exists a level of scientific seriousness and real funding that transforms concepts into concrete experiments. Breakthrough Starshot is not science fiction. It is a program with real financial backing, dedicated to solving the engineering challenges of a laser sail for nanoprobes. The challenges it revealed in attempting to build functional prototypes are exactly the kind of knowledge that must exist before any greater breakthrough becomes possible. Controlled failure is, in frontier engineering, often more valuable than premature success. Advances in plasma physics, ultra-high temperature materials, electronic miniaturization, and space medicine are creating conditions that, even without directly solving the interstellar problem, are making possible solutions that were unthinkable just 20 years ago. Research into pulse nuclear propulsion using controlled fusion microexplosions is being studied in serious laboratories. The development of ultra-thin films for laser sails is advancing in materials laboratories across multiple universities. Our understanding of the biological effects of cosmic radiation is deepening through ongoing missions aboard the ISS and the planning of a return to the Moon. None of these advances, on their own, solves the interstellar problem, but each one closes the gap between what is possible on paper and what is possible in reality. And it is precisely this gradual narrowing that defines real scientific progress at the genuine frontiers of human knowledge. What is perhaps more significant than any specific technical breakthrough is that the conversation about interstellar travel has left the exclusive domain of science fiction and entered the realm of serious physics and engineering. With peer-reviewed publications, specialized conferences, and research programs built around concrete objectives. This is not a fast process, and no one working rigorously in this field makes optimistic predictions about crewed interstellar spacecraft within the next century. But it means that the obstacles that once seemed insurmountable are being mapped with ever greater precision. And an obstacle mapped with precision is qualitatively different from one that merely seems impossible because no one has ever truly tried to calculate it. The history of science is filled with boundaries that appeared permanent right up until the moment someone examined them closely enough to see exactly where there was room for a solution. There is something deeply revealing about the nature of the problems an interstellar spacecraft exposes. Every layer of difficulty, energetic, structural, biological, psychological, philosophical, is simultaneously a frontier of human knowledge that has never been crossed under real conditions. Building an interstellar spacecraft is not merely an engineering challenge. It is a project that would demand simultaneous breakthroughs in plasma physics, advanced materials, space medicine, molecular biology, long-duration isolation psychology, and the ethics of committing future generations to a mission they never chose. No other technical challenge our civilization has ever set out to solve has demanded such sweeping breakthroughs across so many distinct fields at the same time. And that is precisely what makes it so extraordinary as an intellectual endeavor, regardless of when or whether it will ever be achieved. When you look up at the night sky and see a star that appears close, perhaps Alpha Centauri, visible from the southern hemisphere as a bright point of light just below the Southern Cross, what you are seeing is light that traveled 4.37 years at 300,000 kilometers per second just to reach your eye. The light arriving at your eye in that moment left that star before you were born. The vast majority of stars visible to the naked eye lie tens, hundreds, or thousands of light years away. Every point of light in the sky is a destination that demands, in order to be reached, solutions humanity does not yet possess. But perhaps the most revealing fact of all is this: we are the only species on this planet that looks at those points of light, understands what they are, calculates their distance with mathematical precision, enumerates the obstacles with physical rigor, and then keeps trying anyway. That alone says something profound about who we are and what drives us. The answer to whether we will ever reach the stars may depend less on any engine or fuel we have yet to invent, and more on that singular trait, our refusal to accept distance as final. If you could choose any star in the sky to visit, regardless of distance or time, which would it be and why? Tell us in the comments. We would love to know. And if you want to keep exploring where physics and the cosmos converge like this, subscribe so you never miss the next video, and share it with that person who also spends their nights gazing at the sky, wondering what lies beyond.